The second derivative test is a similar process. It's just what will divide up our intervals are inflection points. And then we're using our second derivative to talk about concavity. So in fact, even to go back a video or two, nope, just the last one. Inflection point, let's talk about that real quick. So that's where we switch from concave, or between concave up and concave down. So in this case, what we have is a shape that's generally concave down, so similar to a parabola opening downward, and then we switch to something where we have a parabola opening upward. And that point where we're switching is our inflection point. So an inflection point is where we switch concavity, and inflection points occur where our second derivative is equal to 0. So it's like how we find critical points where the first derivative equals 0, inflection points occur where second derivative equals 0. Okay, so if that second derivative is positive, oh yeah, we'll come back to this in a moment because we can use this to talk about our local extrema, but I want to hold on to that till we get there. Let's start with finding our second derivative test. So the process that we can go through is starting with our function. We can go through the first derivative test. And what we could do is from that collect intervals of increasing, decreasing. We could also get our critical points. If we're not sure about whether they're minimums or maximums yet, we could wait until we get to the second derivative test and evaluate then, where we talk about concave up or down, and then we could describe our relative extrema here, or in the first derivative test. I mean, we did that no problem. I tend to use second derivative test for finding local minima maxima if the derivative isn't too terrible to take. So since we already did finding the relative extrema with the first derivative test, let's go through it with the second derivative test. So find all relative extrema for f of x equals x cubed plus 3x squared minus 4. We're going to talk about intervals of increasing, decreasing, and we're going to talk about concave up or concave down. So where we start is with critical points. So we're going to take our first derivative, which is 3x squared plus 6x, and that's it. We want to see where this is equal to 0. I'm going to go ahead and factor out a 3x, which will leave me with an x plus 2. So let's see, we're getting 3x equals 0 or x plus 2 equals 0. So we have critical points at x equals 0 and x equals negative 2. So in terms of our first derivative test, I'm looking at intervals of increasing, decreasing. We're going to have 3 intervals where it's less than negative 2, between negative 2 and 0 and 1. So let's go ahead and make this table for increasing, decreasing. So our intervals, we have negative infinity to negative 2, we have negative 2 to 0, and we have 0 to infinity. And this one is where with the first derivative test in that first video, I kind of separated the steps up. I'll show you how I just kind of jump ahead a little bit here. I'm going to evaluate the first derivative in each of these intervals, choosing a test value that's in that interval. So I'm going to look at negative 3, how about a negative 1, and how about a positive 1. And then what I'm doing is I'm plugging into our first derivative function, which is right over there. So if I plug in negative 3, that'll be 3 times 9, 27, minus 18. All I care about is that it's coming out positive, which tells me our function's increasing right there. If I plug in negative 1, that'll be a 3 minus 6. That'll come out negative, so decreasing. And if I plug in positive 1, that'll all be positive, so we're increasing. So intervals of increasing, negative infinity to negative 2, and 0 to infinity. And then for decreasing, that'll just be occurring -2 to 0. And from there, let's go to our second derivative test. So first thing I'm going to need is the inflection point. That's going to separate up my intervals here. So inflection point is going to occur where our second derivative is equal to 0. So second derivative, if I go back to my first derivative function and take the derivative, that'll be a 6x plus 6. Solve for where that equals 0. Let's see, factor out a 6 for x plus 1. So we'll have x equals -1 as our inflection point. So for our intervals here, we have this division at -1. So we're just going to have two intervals, below -1 and above -1. So let's go ahead and make our concavity table. So our two intervals, we're going -infinity to -1 and -1 to +infinity. And I want to evaluate the second derivative in each of those intervals. Now this is a spot where I kind of combine the relative extrema work that I'm going to do with this. You don't have to. You can go through the same process of just choose anything in those intervals. What I like to do is go back and look at those critical values. So we have x equals 0 and x equals -2. And if I can use those values, I sure do like to. So -2 fits there, 0 fits there. So just knowing those are critical points, and those are nice numbers for those intervals anyway, but I'll tell you in a little bit why. So I'm going to take that and plug it into our second derivative function right here. So 6 times -2 is a -12 plus 6, that's going to come out negative, which tells me we are concave down. And then at the second derivative of 0, that will be a +6, so we are concave up. So this gives me intervals for concavity. So we're concave up from -1 to +infinity, and concave down from -infinity to -1. Now let's talk about our relative extrema. So at x equals -2, that was one of our critical points, we are concave down, which means we have this general shape, which means if that's a critical point, that's occurring right at the peak there. So that is going to be a local max. So we can use concavity to know that it is reaching a highest peak there because it's concave down. And then at x equals 0, we're concave up. So that means we're making a local minimum. So you can use concavity with those to get the general shape and use those. We could confirm it with our first derivative test. Like here's our x equals -2. Here's our x equals 0. So going from increasing to decreasing, that's going to make a maximum. Decreasing to increasing will make a minimum. So we could have seen it there, just like this, for showing how we could get it from the concavity table as well, especially if we don't have to do the first derivative test to get to the second derivative test. If we were just interested in concavity and relative extrema, I would skip this second step right here. I would just get those critical points that I know about the relative extrema, go ahead and get that inflection point, set up the table, and then evaluate those relative extrema. But because this one asked about increasing, decreasing, we had that little extra bit with the first derivative test. Okay, so just to bring it back together, where our second derivative is positive, if that's a critical value right there, it's making a relative minimum or local minimum. Because if it's positive, it's concave up, which will always make a minimum. Whereas if our second derivative is negative, we have concave down, which always makes a maximum. And if our second derivative is equal to 0, our test fails, and you'll want to go back to the first derivative test to see what's going on there, what's happening. Could be a discontinuity. We could also go to the graph and see what's happening there. Okay, so found our critical values for the relative extrema, evaluate the second derivative, and determine the sign. And with that, we can define our relative extrema. We could also define intervals of concave up or concave down. And I was making that sound like we were done when we have another example here. So let's go through this example too, maybe a little quicker. In fact, let's take out the increasing, decreasing for this one so that we can really just focus on that second derivative test. So we're looking for relative extrema and concave up versus concave down. So first step, critical points. So we're going to take our first derivative, which is a 15x to the fourth plus a 15x squared. Yep. Okay. And then we want to see where this is equal to 0. So let's see, we can factor out a 15x squared, and that would leave us with x squared plus 1, which will give us x equals 0. And if we try to solve x squared plus 1 equals 0, we're going to run into issues by trying to take the square root of a negative. So that's not going to give us anything there. So critical points in terms of relative extrema is going to be an x equals 0. And in fact, I'm just going to grab that to the side here. Relative extrema is occurring at x equals 0. And then we'll talk more about what's happening there as we go forward. Okay, let's go on to inflection points. So now we're going to take the second derivative and see where that equals 0. So let's see, that'll be 60x cubed plus 30x. And solving for where that equals 0, let's factor out a 30x, which would leave us with 2x squared plus 1. And that'll give us x equals 0. And we're going to run into the same issue with the negative there, so that's not going to give us anything. Okay, so using the inflection point of x equals 0, let's see what's happening with our intervals. So we're making a concavity table, and our only dividing value is 0, so we're going to go from negative infinity to 0, and then 0 to infinity. And we are going to evaluate the second derivative, and how about a negative 1? And how about a positive 1? Okay, so with this, if I plug in if I plug in negative 1 to our second derivative, so let's see, that'll be a negative 60 plus 30, so that's going to be negative, so that's concave down. And then if I plug in positive 1, that will be positive, so concave up. So we're doing something like this, and then switching to something like that. So something I'm going to notice here, like I was talking about up here, like I tried to plug in those critical points. I can't do that here because 0 is not being included. So I couldn't plug in 0, and it's because if I try to evaluate the second derivative at 0, so at our critical point, I'm just going to get 0 out. So this is the case that we want to be careful of. This is where the test fails, and we want to go and look at the first derivative test. So even though I tried to bypass it, we got to go look at it. And something that I'm seeing here is at 0, we're switching concavity, so this just might be a true inflection point where our graph is turning. But let's take a quick look at our first derivative test. So same intervals of negative infinity to 0 and 0 to infinity, but now I'm going to take a look at what's happening from our first derivative, and let's go ahead and plug in -1 and first derivative at +1. So at -1, that should all be positive, so our graph is increasing. And for our first derivative at +1, that should also be positive. So notice it doesn't change increasing to decreasing. It's going up and then it keeps going up. Now, if we're concave down and increasing, what we're seeing is this part of the graph. That's the part that's increasing and concave down. And then concave up and increasing is this part of the graph. So if we kind of smush those together of increasing concave down and then switching to increasing concave up, that's our inflection point. Switching concavity, but it is not creating a local minimum or maximum. So with all of this, we can talk about how the intervals are concave up, concave down. In terms of relative extrema, there are none. We investigated it, and it is not a local minimum or maximum. It's just a true inflection point where our graph is not turning. And then if we look at our graph in Desmos, what we could see is this, which shows us there's no local minimums or maximums. It's just increasing, and then it just keeps increasing.